and EW926 has acknowledged the undefinability he's acknowledged the idea that 0 times infinity is essentially undefined, and that's actually a long-standing principle. So what we do in calculus now is we have the concept of limits, where we would say as the limit as n approaches infinity, 1 over 2 to the power of n approaches 0. Okay, so that's a long-standing idea in calculus. I imagine most of you watching this probably have taken calculus, and I maybe assume knowledge on that, and I apologize, but the whole idea of limits is based on Lord Berkeley's objection to the calculus of Newton and Leibniz and the whole idea of infinitesimals. And his objection is, well, wait a second, what really is an infinitesimal? How do you have something infinitely small and yet consider it something other than just nothing, or something other than just 0? Okay, so the idea of limits was introduced to answer the objections of the philosopher Lord Berkeley. Actually, it'd be Berkeley, I believe is how you would pronounce his name. Okay, we in our country here we pronounce it as Berkeley, and we have the city of Berkeley in his honor. And so what they introduce is, okay, instead of saying 1 over 2 to the power of n equals 0, we say the limit as n approaches infinity, comma 1 over 2 to the power of n approaches 0. And this is a long-standing idea in calculus. However, when you get to Cantor and you get to some of the ideas he was exploring, he was going beyond the idea of limits. And he was going into the idea of the thing in itself. And this is a long-standing disagreement in philosophy of the phenomenon, okay, or how something might appear to us versus the thing in itself, or some might use the term the noumenon, although philosophers even disagree as to whether the term noumenon should mean thing in itself. It's a very complicated subject. I definitely can't do it justice on a lazy Sunday afternoon here in my kitchen. So suffice to say, this would be the concept of limits as n gets ever bigger, 1 over 2 to the n gets ever smaller, or 1 over n would get ever smaller, or 1 over n squared would get ever smaller. Now, n, if it were just n would get ever bigger. 2 to the n power would get ever bigger towards infinity. Okay, now calculus doesn't distinguish between levels of infinity, because calculus deals with limits, or it deals with the reality of as it approaches the limit of infinity, such and such will happen. It does not actually get to the idea of the thing in itself. And this was the question that I was addressing here. What is 0 times 2 to the Aleph naught power in itself? Okay, now here is where I go into what could very well be uncharted territory, and it might very well be that it's wrong, but I'm going to go give a stab at it. Right here I have, let's take the number line between 0 and 1, okay? And this is supposed to be every conceivable rational number between 0 and 1, okay? You notice I have discrete check marks here? Okay, so you can say, well, the limit as n approaches Aleph naught, 1 over n, meaning 1 over n would be kind of like the infinitesimal. It would be kind of the difference between this notch and this notch approaches 0. Okay, now that would be the calculus way of putting it, but the problem is when you actually examine the thing in itself, it gets to the paradoxes of the infinitesimal that Lord Berkeley thought up. And so, and the Cantor further expounded on when the whole idea of Cantor dust and the Dedekind cut, and again, it's a very complicated history, but let's make it really simple, okay? All rational numbers between 0 and 1, and we'll just pretend that well, we have an infinite number of dots between 0 and 1, okay? Well, you can think of that as the difference between these two as 1 divided by Aleph naught, in a sense, okay? The mathematicians will hate that, but what you're really doing is you might be taking, 1 divided by 2, okay, 1 divided by 3, 1 divided by 4, 1 divided by 5, such and such and such, until you get you get to 1 divided by a countable infinity. In other words, an infinity that you can arrive at with the cardinal numbers, and you would have something roughly akin to every rational number between 0 and 1. It's a little more complicated than that, but the bottom line is you have discrete differences between these various knots that would be infinitesimal, but you could look at it that way, and you would have a difference between 0 and, let's say, the rational number above 0. Now, there are paradoxes involved with that. What would the difference be? Would it be 0? I mean, of course it would be 0. But the point is, you can still see a discrete, countable, almost like a jump of rational numbers between 0 and 1. You could never really figure out what the next rational number above 0 is. But you could say that there is a 0-1 binary dichotomy here between 0 and the rational number above 0. Okay? As paradoxical as that is, and as much as that bumps into some of the objections of Berkeley, you could say it at least in some abstract theoretical sense. And so you could say, oh, okay, well, you could possibly divide by all if not. But what about and we would say in calculus, the limit as n approaches 2 to the all if not, well, 1 over 2 to the all if not would be 0. But what about the thing in itself? Can you actually divide by 2 to the all if not? And I would suggest no. And the reason why is because any time you are dividing by something, you are essentially chopping it up into pieces. It's a simple way of putting it. If you take 1 over 2, you are chopping 1 into 2 pieces. 1 over 3, you are chopping 1 into 3 pieces. 1 over 4, 4 pieces. 1 over all if not, you are chopping 1 into infinitely many pieces, infinitesimal, but each being discrete. If I look at it from the standpoint of the continuum, something very strange happens. I can't really divide it by c, because the whole idea of discrete countable entities disappears now. What really is the next number? Not next rational number, but the next real number above 0. That's too paradoxical, but because between 0 and the next rational number above 0, there are infinitely many real numbers. And those infinitely many real numbers are themselves not discrete, this number, that number, that number. It's more like a continuum. It's more like almost like a wave as opposed to particles, to use the metaphors of quantum mechanics. And so I maintain that it would not, although the limit as n approaches to the all if not power, 1 over 2 to the all if not power would be 0, I maintain that the actual thing in itself is impossible. It's impossible even to consider, and therefore the flip side of it is to say, well, what is 0 times c? That would also be impossible to consider, really, for any level of infinity above that of all if not. That would be my argument, heuristically stated. It's not proven, but I would hope that mathematicians would at least consider it. And on that, not yet. I would say that, and I want to end this by saying I thank EW926 for a very kind response video, and I want to also encourage him to please, he says he's only 16, and I would say, hey, you're only 16 years old. In a few years, you're going to be going to Cal or Stanford or someplace doing very advanced stuff. And what I'm going to ask of you is to take me up on my challenge. Even if you don't believe in the continuum hypothesis, maybe take some of these ideas and run with them and see what you might find. Be my advocate. Kind of like a philosopher advocate, where you may not even agree with a position, but you're willing to take it on. So that's my challenge to you, EW926, and thank you for subscribing. Take care.